Hello everyone, today I'm going to talk about the introduction to index notation. So we use index notation to simplify our equations. Index notation is developed based on rectangular Cartesian coordinate or RCC, but it's applicable to other coordinates as well. We have two different types of indices, whether they are lower index or it's called covariant or subscript, such as here, this lower index, or upper index, contravariant or superscript. So here we are dealing with lower index, which is the most common type of indices that we use in our formulations. We're going to use Einstein Summation convention, which says that a term in an equation is a component that is separated by plus, minus, or equal sign. So it's not multiplication or division. So here, for example, in this equation, this A is a term, then we have a term here. Then on the other side of the equation, we have one term, two term, and three terms. So that's our definition for terms. A repeated index within a term implies a summation of that term. So for example, here, I is a repeated index. It's the same index here. So it's repeated twice. So that means summation for us. And because I is changing from 1 to 3, so we have A1, U1, A2, U2, A3, U3. This repeated index is referred to as dummy index. That's the name that we are going to use. So dummy index indicates summation. And also they can be replaced by any other symbols without any change in their meaning. So here, instead of writing AI, UI, I can write AJ, UJ, or AK, UK, and all of them mean the same thing. Because it's dummy, because it's repeated, I can replace it with any other symbol. So it's a standalone symbol within each term. And as we said, it implies summation. So it's the same as writing sigma I1 to 3. And it simplifies our equations significantly when we use this convention. The other index would be free index. So free index is not repeated. So it's as opposed to dummy index. If it's repeated more than once, it's a dummy index. Repeated, if now repeated would be free index. The number and symbol of free indices on each side of the equation has to be the same. So here we have AI, I is not repeated, so that's a free index on the left side. Bij, Cj, J is repeated, so J is a dummy index, I is a free index. Here, K is repeated, and I is a free index. So you can see the symbol and the number of free indices on the right side of the equation is the same as left side of the equation. If it's not the same, like this, it's meaningless. We don't have any convention for that. We don't know even what that means. So the equation would be incorrect. Our indices would be incorrect if the number or the symbol of the free indices won't be the same in each side of the equation. The feature of free indices is that they allow us to expand equations. They allow us to multiply equations. Dummy indices had summation within a term. Free indices allow us to write multiple equations. How many equations depends on how many free indices we have. So 3 to the power of number of free indices. And this 3 comes from 3 dimension. We are dealing with 3 dimension. So if we have one free index, that would be, we can write 3 equations. So let's look at an example here. Fi sigma ij aj. So we have free index here, I. We have a dummy index. We're going to see how they react, where I and j changing from 1 to 3. So I start with my free index. We said that free indices multiply equations. So here I1, I2, and I3. We have 3 equations because we have one free index. And j is a dummy index, so indicates summation within a term. So here I start F1, sigma 1, 1, A1. I need to sum. So sigma 1, 2, A2, sigma 1, 3, A3. Similar to for I2. F2, sigma 2, 1, A1, 2, 2, A2, 2, 3, A3, and so forth. So that's the feature of free and dummy indices. So we represented all these 3 equations by just this simple equation here. So that simplified our equation significantly by just two simple definition of free and dummy indices. So looking at this equation, this is just a equation of the equivalent force for each stresses. So if you have stresses on each surface, you want to find the resultant forces in direction 1, then you know you have to deal with sigma 2, 1, A2, you have to deal with sigma 1, A1, and sigma 3, A3. So that's what this equation represents. Forces, all the force, the total, the resultant force of stresses acting on a surface. The other definition is a Kronecker delta, which is a second order tensor, and is defined as 1 when I and j are the same, and 0 when I and j are not the same. So if these two indices are the same, that would be 1, otherwise it would be 0. It's a very powerful function to zero out the terms that we don't want. In terms of matrix, because it's a second order tensor, we can write it in a matrix form. And here ij 1, 1, 1, when the all the components in diagonal are 1, and outside that would be 0. If I want to write delta ii, so that would be ii, we have two same indices, so I is a dummy index, so that indicates summation. So sigma ii means sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3. What is, sorry, delta 1, 1, delta 2, 2, and delta 3, 3. So what is delta 1, 1? First row, first column, that's 1. Delta 2, 2, second row, second column. And delta 3, 3, third row, third column, 1 plus 1 plus 1, 3. Or we could go to the definition that we said here. The indices are the same, so it's 1. The indices are the same, so it's 1. One feature of the Kronecker delta is that it removes the dummy index. So here, delta km tmj would be equal to tkj. It removes this m, which is a dummy index. Same thing for here. It removes k, or it could remove m, and we would have delta kk. So that's a feature for simplifying our equations. So let's look at a more complex equation. So here is an elasticity equation for isotropic material relating stresses and strength, or Hooke's law. So here we have sigma ij, it's a stress tensor, second order tensor, two indices, 2 mu epsilon ij plus lambda delta ij epsilon kk. So we have free indices, we have dummy indices, and we have a Kronecker delta. That's a perfect example. Mu and lambda are Lama constants. So it's just a constant that we use in elasticity equation. And they're based on elastic modulus, Poisson ratio, and shear modulus. It's just easier to write it in terms of Lama constant than these elastic constants. So it's nothing specific about them. It's just our constant values. And here, let's go to our equation. I and j are free indices here. They're not repeated. So the number of free indices on the right side should be the same. Here, I and j are free indices. Here, I and j again are free indices in this term. Epsilon kk is a dummy index, means summation over a term. So let's go and write our equations. First, how many equations can we get? Because we have two free indices. If you remember, the equation is 3 to the power of 2, so that would be 9 equations. So this equation is gonna represent 9 equations for us. Let's just start with the first one. I equals 1, j equals 1. These two are free indices. K is summation, so it's changing from 1 to 3. So sigma ij, sigma 1, 1, 2 mu epsilon 1, 1, plus lambda delta 1, 1. I mean, here we know it's a Kronecker delta, so 1, 1 is 1. So this would be 1. And then epsilon kk. So that's the dummy index. That means summation. Epsilon 1, 1, 2, 2, 3, 3. Same thing for 1 and 2. So here we have epsilon sigma 1, 2. That's the shear stress. When the indices are not the same, it's a shear stress. Here we are dealing with normal stress. 2 mu epsilon 1, 2 plus lambda delta 1, 2 epsilon 1, 1, 2, 2, 3, 3. But we know delta 1, 2 is 0 because the indices are not the same. It's not on the diagonal. So that would be 0. So that means that the whole term will go away. So it zeroes out the second term. And then we only have 2 mu epsilon 1, 2. And if you go back to the definition here, you know, the shear stress is G gamma 1, 2, and then gamma 1, 2 is 2 epsilon 1, 2. So we are getting our stress equations just by this equation. And if I want to write the other terms, these are all complete 9 components. So this equation representing all the equations here. So if you're not sure whether index notation is helpful at all, this should have convinced you that we can simplify equations significantly by just, again, 2 definitions, free and dummy indices. And you can see this is a normal stress. And these are the shear stresses, which only relate the corresponding shear strain and shear stresses. So let's look at a numerical example as well. Here, if we have a second order tensor, it's given in terms of a matrix, we want to find TII. I, the dummy index, is repeated, so that means summation. T11 plus T22 plus 333. What is T11? The first row, the first column is 4. Then the second row, second column, 0. Third row, third column, 3. So that would be 7. And then here we have TII, TKK. So we have one dummy index and one dummy index here. So that would be, we already found TII is 7, TKK is the same thing. Again, we said that because if it's dummy, we can change the symbol. So that would be 49. If you want to write it out, you can do that. If you are in doubt whether you can do that or not, you can just simply write it out to see actually whether you get the same answer. And then that would be 49. That would be the same answer. So if you want to summarize our index notation lecture, we can say that first of all, it's important what we say by term. That has to be the component that is separated by plus, minus, and equal sign. An index that appears once is a free index, appears more than once is appears twice is dummy index, appears more than twice is meaningless. So it can only appear either once or twice. Free indices multiply equation, dummy indices can be replaced with other symbols and also indicate summation. The number and symbol of free indices has to be the same on each side of equation. And Kronecker delta is very powerful for zeroing out the terms that we don't need. So we saw that functionality when we looked at shear stresses. They zeroed out the normal strain components.